So, welcome to lecture series on nonlinear programming. We have seen that what convex functions are and also some of their properties. Now, we will see some more properties of convex functions. So, in our last classes we have seen that we can prove a function to be convex function simple by definition of a convex function, or we can use the definition of epigraph, because if a function is a convex function if and only if its epigraph is a convex set, or if function is once differentiable on a open convex subset S of Rn, then f is a convex if and only if f of x1 minus f of x2 is greater than equals to x1 minus x2 transpose gradient of f x2. Okay. So, these three properties we have defined for the convex function. Now, we will see that if function is twice differentiable, then what is the property for convex function? How we will see that a function is convex or not. Okay. So, before studying twice differentiability of a convex function, we will see the definiteness of a symmetric matrix H. So, a symmetric matrix H of order n cross n is said to be positive semi-definite if x transpose Hx is greater than or equals to 0 for all x in Rn. Negative semi-definite if x transpose Hx is less than or equals to 0 for all x in Rn. Positive definite if this inequality hold as strict inequality for all x in Rn, x should not equal to 0, and it is negative definite if this inequality for negative semi-definite hold as strict inequality x should not be for all x in Rn and x should not equal to 0. So, what these are, let us discuss this by few examples. Now, suppose we have this matrix H. What the matrix H is? This is 1 minus 1 minus 1 1. They are symmetric matrix and this having the order 2 cross 2. Now, let us find x transpose Hx. Since this is of order 2 cross 2, so x transpose will be x1 x2, it is 1 minus 1 minus 1 1, and x is x1 x2. Okay, we are taking x as x1 x2. So, x transpose will be x1 x2 as a row vector, H is this matrix and x is a column vector. Now, you multiply these three. So, what we obtain when you multiply these three? So, it is x1 minus x2, it is minus x1 plus x2, and this is equals to x1 minus x2 plus x2 minus x1 plus x2, which is equals to x1 square plus x2 square minus 2 x1 x2, and this is x1 minus x2 whole square. And of course, this quantity is greater than or equal to 0 for all x1 and x2. Okay. So, we say that this matrix H is positive semi-definite. Semi-definite. Okay. This matrix X is positive semi-definite. Since there exists some non-zero x also where it is equal to 0, like 1 comma 1, 1 1, it is equal to 0. So, we can't call it positive definite, because for positive definite, as we see in the definition, positive definite this must be greater than 0 for all x in Rn and x should not equal to 0. Okay, this must be positive strictly greater than 0. However, this is greater than or equal to 0, and there are non-zero x where it holds as an equal to 0. So, therefore, it is not positive definite, however, it is positive semi-definite. Okay. Now, we take another example. You take identity matrix of order 2 cross 2, I 1 0 0 1, and when you take x transpose Ax, so it is nothing but x1 square plus x2 square. You can simplify this. It is strictly greater than 0 for every x in R2. because it is 0 only when x1 x2 both are 0 and x should not equal to 0. So, that is not here. So, that means it is strictly greater than 0. So, therefore, this matrix is positive definite matrix. Now, from these definitions you can easily see that if a matrix H is positive semi definite, then minus of H will be negative semi definite, because when you multiply with minus 1 both the sides, then minus of H will be definitely negative semi definite. And similarly, if a matrix H is positive definite, so negative of H will be negative definite, because this inequality hold. So, that is there in this note. Symmetric matrix is negative semi definite or negative definite if and only if negative of H is positive semi definite or positive definite respectively. Okay. Now, how can we check whether a given matrix is positive definite, positive semi definite, negative definite or negative semi definite? So, we have two tests. First is eigenvalue test. Okay. Now, since the given matrix A is real and symmetric matrix, so we know that if a matrix is a real and symmetric matrix, then all its eigenvalues are real. So, it is of order n cross n. This means it will be having n number of eigenvalues, lambda 1, lambda 2 and lambda n, and all will be real. Then A is positive definite if and only if all its eigenvalues are strictly greater than 0. Okay, you find all the eigenvalues of the real symmetric matrix A. If the all the eigenvalues are strictly greater than 0, then we say that it is positive definite. Positive semi definite if and only if all eigenvalues are greater than or equal to 0. Negative definite if and only if all eigenvalues are strictly less than 0. Negative semi definite if and only if all lambda i's are less than or equal to 0, and indefinite, okay, if and only if some lambda I are greater than 0 and some lambda j's are less than 0. Now, finding an eigenvalues always is not a simple task. If we have a matrix of order 4 cross 4 or 5 cross 5, then always finding eigenvalues of a matrix to check the definiteness of a symmetric matrix A is not an easy task. So, we have another test also which we call as principal minor test. Now, what it is? First we understand what principal minor is, then we go to a test, that how using this test we can check, we can find whether a matrix A is positive or negative definite. Okay. So, a minor of matrix A of order k is principal, which you call as principal minor, if it is obtained by deleting n minus k rows and n minus k columns. You delete n minus k rows and n minus k columns from a n cross n matrix, you got a matrix of order k cross k. The determinant of that matrix is called principal minor matrix. Okay. The leading principal minor of A of order k is the minor of order k obtained by deleting the last n minus k rows and columns. We will understand this by an example. Okay, what this means? Let us understand this by an example. Suppose you have matrix given here A equal to 1, 2, 3, 4. If you delete, it is 2 cross 2. Okay. And you have to delete n minus k rows and columns from the last. Okay. Now, n is 2. Suppose k is, in this case k is either 1 or 2. Okay. Suppose k is 1, 2 minus 1 is 1. So, you delete last one row and one column, you delete last one row and one column. So, you will left with D1 means principal minor of order 1, which is 1, which is this element. Now, when you take D2 is simply determinant of n minus, you do not delete any rows and columns, 2 minus 2 is 0. So, that means the full matrix 2, 3, 3, 4. that is nothing but 4 minus 6, which is minus 2. So, this is how we can find the determinants of leading principal minors. Okay. So, here dk represent leading principal minor of order k. Okay. Suppose you have a matrix B of order 3 cross 3, you can take any matrix 1 2 3 0 4 2 minus 1 2 3 2 4. Suppose you have this matrix. Now, suppose you have this matrix B. So, what D1 means? D1 means you start from the first element and take a determinant of order 1 cross 1. Okay, so that is 1 only. Now, D2 is simply you start with this element, take the matrix of order 2 cross 2 and take its determinant, so that is 1 2 0 4, which is nothing but 4, and D3 is nothing but determinant of 3 cross 3 matrix, which is itself, that is 1 2 3 0 4 2 minus 1 2 4. So, this we can find, this will be D3. So, that is how we can find out the principal leading principal minors. Okay. Now, finding leading principal minors, how can we check whether a matrix is positive definite, negative definite or semi definite? So, let us see the result here. Let A be a symmetric n cross n matrix, then A is positive definite if all the leading principal minors of the matrix A are strictly greater than 0. Okay. It is positive semi definite if and only if D1 is strictly greater than 0 and all other principal minors are greater than or equal to 0. It is negative definite if and only if D1 is less than 0, D2 greater than 0, that means minus 1 raised to power n, Dn is strictly greater than 0, and negative semi definite if and only if D1 is less than 0, D2 greater than equal to 0 and so on, such that this quantity is greater than equal to 0. Okay. We have the alternate signs in negative definite because a matrix, if a matrix A is negative definite, that means negative of A is positive definite. If a matrix A is negative definite, this means negative A is positive definite. And what is the determinant of negative of A? That is nothing but minus 1 raised to power n, determinant of A, that we already know by the properties of determinant. Okay. Now D1 is of order 1 cross 1, so it will be negative because you substitute n equal to 1 here, and D2 is of order 2 cross 2, so it will remain positive. Okay. And D3 is of order 3 cross 3, and when you substitute n equal to 3, so it will become negative. So, from here we can conclude that if we have a positive definite, that is all leading principal minors are strictly greater than 0, then for negative definite we have an alternate signs. Okay. Now, let us see some examples based on this to check the definiteness of a matrix A. Now, suppose Q is a matrix and Q is given by, it is 8 4 4 2. So, what will be D1 here? D1 is 8, 1 cross 1, which is strictly greater than 0. What is D2? D2 is determinant of 8 4 4 2, which is 16 minus 16, which is 0. So, D1 is strictly greater than 0 and D2 is equal to 0. That means, by this test, what we can say? By this test we can say that it is positive semi definite, because D1 is strictly greater than 0 and D2 is greater than equal to 0. So, we can say that the matrix Q is, this implies matrix Q is positive semi definite. Okay. Now, we take another example. Suppose we have matrix A here. Okay. Now, what is matrix A? You can easily see the matrix A is 3 0 3 0 1 minus 2 3 minus 2 8. Now, when you take D1, D1 is a leading principal minor of order 1 cross 1, which is 3. and it is strictly greater than 0. D2 is leading principal minor of order 2 cross 2. So, that is determinant of 3 0 0 1, which is 3 only and greater than 0. Now, D3 is determinant of the full matrix A, which is 3 again, and it is strictly greater than 0. All the leading principal minors are strictly greater than 0. This means matrix A is positive definite, okay, because of this result. Positive definite if and only if all principal leading principal minors are strictly greater than 0. Now, we have the result for the convex function. Okay. We understand what positive semi definite or positive definite means. Now, we can state a result for a convex function. Let S be a non-empty open convex subset of Rn, and f is a function from S to R be twice differentiable on S. Okay. Then f is a convex function on S if and only if the Hessian matrix, which is gradient square f x, is positive semi definite for all x belongs to S. So, this is Hessian matrix we have already defined. So, f is a convex function on S if and only if Hessian matrix of f on x is positive semi definite on S. So, now we have to show that if f is a convex function, then this result hold, and if this result hold, then f is a convex function. So, let us try to prove this result. So, let f be a convex function on S. So, we have to prove that a function is twice differentiable, then the Hessian matrix is positive semi definite. That means, we have to show that for any x, x transpose gradient square of f x, x is greater than or equal to 0 for all x in S. This we have to prove, okay, because we have to show that this is positive semi definite. Okay. So, let x bar belongs to S. Now, since S is an open convex subset of Rn, here then for any given x in Rn, there exists some lambda bar greater than 0 such that x bar plus lambda x will definitely belongs to S for lambda between lambda bar and 0. You see that S is an open convex subset of Rn, okay, and x bar is some fixed point in S. Okay. Now, for if this is an open convex subset of Rn, so for any given x, you take any arbitrary point x in Rn, there will always exist some lambda bar, no matter how small it may be, but there will always exist some lambda bar such that this point, which is x bar plus lambda x, will definitely belongs to S for lambda between 0 and lambda bar, because S is a open set. Okay. Then for the small value of this lambda, this x bar plus lambda x will belongs to S. Now, since f is a convex function, so we know that f of x bar plus lambda f x will be lambda x will be equal to f of x bar plus lambda x transpose gradient of f x bar. Because if function is convex, this means f of x1 minus f of x2 is greater than or equals to x1 minus x2 transpose gradient of f x2 for all x1 x2 in S. This we have already seen, this property we have already seen, that if f is a convex function, then f of x1 minus f of x2 will satisfy this property for all x1 x2. Now, suppose this is x1 and this is x2. This belongs to S and this also belongs to S. This belongs to S and this belongs to S. So, this will hold, this property will hold for this also, because f is a convex function. So, f of this will be equal to f x bar. So, this is x 1, this is x 2 plus x 1 minus x 2, which is lambda x gradient of f x. Okay. So, it is not equal, this is greater than equal to. Okay, because f is a convex function. Now, now since f is a twice differentiable for all points in S, so we can apply definition of twice differentiability. So, by the twice differentiability, what we obtain, f of x bar plus lambda x will be equals to f of x bar plus lambda x transpose gradient of f x bar plus 1 by 2 lambda x transpose gradient square of f x bar into lambda x plus beta into x bar and x, which is it is lambda x and x bar and norm of lambda into x whole square. This is by definition of twice differentiability of f. Okay. Now, when you take this quantity, when you apply this condition in this expression 2, so what we obtain? Now, where this tending to 0 as lambda tend to 0. Okay, this is by the definition of twice differentiability of f at x bar. Okay. So, now you apply the definition 1, condition 1 on this expression. So, what we obtain? So, this implies from 1 and 2, what we obtain, that 1 by 2 lambda square x bar gradient of square of f x bar into x plus beta into lambda x into x bar into lambda square norm of x square is greater than or equal to 0. Because this quantity when you take on the left hand side is greater than or equal to 0. Okay. Now, you can divide by lambda square both the sides. So, what we will obtain? We obtain 1 by 2 x transpose gradient square of f x bar into x plus beta lambda x bar norm of x square is greater than or equal to 0. Okay. Now, take lambda tend to 0 both the sides. When you take lambda tend to 0, so this quantity beta lambda x bar will tend into 0. So, this implies x bar transpose gradient square of f x bar into x 1 by 2 will greater than or equal to 0, because this when you take lambda tend to 0 both the side, this will tend into 0, okay, and this is 0. So, this quantity will be greater than or equal to 0. So, this implies x transpose gradient square of f x bar will be greater than or equal to 0, and this implies gradient square of f x is positive semi definite on S. Now, if it is positive semi definite at x bar belongs to S, you can vary x bar. So, we can get that this Hessian matrix is positive semi definite on S, that is for every x in S. Okay. So, this is how we can obtain that if f is a convex function, then its Hessian matrix is positive semi definite. Okay. Now, we will try to prove the converse part of this theorem. Converse part means assume that the Hessian matrix is positive semi definite on S, and we will try to obtain that the function is a convex function. Okay. So, by the mean value theorem, we have to apply mean value theorem here. By the mean value theorem, since function is twice differentiable, So, it is fx1 minus fx2 is equals to fx1 is equals to fx2 plus x1 minus x2 transpose gradient fx2 plus 1 by 2 x1 minus x2 transpose gradient square of fx2 into x1 minus x2. You can take some x cap here, where x cap is nothing but convex linear combination of x1 and x2. This is by the mean value theorem. If apply mean value theorem in the function f, then by the mean value theorem, since function is twice differentiable, so fx1 is equals to fx2 plus x1 minus x2 transpose gradient fx2 plus 1 by 2 of this quantity, where this x cap is a convex linear combination of x1 and x2. Okay. Now, it is given to us that Hessian matrix is positive semi definite. This means y transpose gradient of fx into y is greater than or equal to 0 for every y in Rn. Okay. This means this result. So, this means now this x cap is in R, because S is a convex set, okay, and this is any point in Rn. So, and since this is an Hessian matrix positive semi definite, so this quantity x1 minus x2 whole transpose gradient square fx cap x1 minus x2 will be greater than or equal to 0, because this is some point in Rn and this is in S, and Hessian matrix positive semi definite on S. So, this quantity will be greater than or equal to 0. Now, this quantity is greater than or equal to 0 means this implies that fx1 minus fx2 minus x1 minus x2 whole transpose gradient fx2 is greater than or equal to 0. So, this implies fx1 minus fx2 is greater than or equals to x1 minus x2 whole transpose gradient fx2. So, this implies f is a convex function on S. So, that is how we can show that f is convex if and only if its Hessian matrix is positive semi definite. Okay. So, we have various examples now to illustrate, to see. Suppose function is from R to R and fx equal to x square. Now, when function is from R to R, what is the Hessian matrix of this function? Hessian matrix is simply second derivative of f. So, second derivative is here is the first derivative is 2x and the second derivative is 2, which is greater than 0. That means it is positive semi definite, and that means function is convex. Okay. Now, similarly, you take f equal to suppose e raised to power x, x belongs to R. You take the first derivative is e raised to power x, second derivative is again e raised to power x, which is strictly greater than 0 for all x in R. So, that means this function is convex function. Okay. In fact, these are strictly convex, because if Hessian matrix is strictly, Hessian matrix is positive definite, then function is strictly convex. Okay, because if Hessian matrix is positive definite, then the function is strictly convex. We have a result this. Okay. Similarly, suppose you have x1 square plus x2 square. So, you find Hessian matrix of this function. Hessian matrix is nothing but del square f upon del x1 square, del square f upon del x1 del x2, del square f upon del x2 del x1 del square f upon del x2 square, and that is nothing but when you take derivative respect to x1 it is 2 0 0 2. So, to check whether this Hessian matrix is positive semi definite or not, we will find leading principal minus d1 is 2 which is greater than 0 and d2 is 4 which is again greater than 0. So, that means this is positive definite, that means function is strictly convex. Okay. So, we have the same result for strictly convex function also, that if Hessian matrix is positive definite, then f is strictly convex on S, but the converse may not be true. Like in this theorem we have if and only if condition, that if a function is a convex function if and only if the Hessian matrix is positive semi definite for all x in S, but for strictly convex we do not have a if and only if condition. We have only the condition that if Hessian matrix is positive definite, then f is strictly convex. Now, why the converse is not true? We have a counter example like x raised to power 4. When you take this is graphically you can easily see that this function is strictly convex, okay. But when you take the second derivative of this function, this is 12x square, we can easily check, and which is not positive definite for x equal to 0. So, converse may not be true, okay. Now, let us check solve few examples using twice differentiability of the function f to see whether the function is convex or not, okay. Now, for concavity, if you want to see the concavity, the function f is a concave function on S if and only if the Hessian matrix is negative semi definite on S, okay. The same on the same lines we can obtain the proof. Now, suppose you have the first example f of x1 x2 which is given as 4 x1 square plus x2 square plus 4 x1 x2. Now, we will obtain the Hessian matrix of this function. What is the Hessian matrix of this function? It is del square f upon del x1 square, del square f upon del x1 del x2, del square f upon del x2 del x1, del square f upon del x2 square. What it is? It is 8, it is 4, 4, 2. Now, what is d1? d1 is 8 strictly greater than 0, and what is d2? d2 is 16 minus 16 equal to 0. So, that implies this del square f is positive semi definite, and that implies f is a convex function. F is a convex function. Now, similarly, you can check for the second problem. Suppose second problem is nothing but is G, which is x1 x2 plus 2 x1 square plus x2 square plus 2 x3 square minus it is 6 x1 x2, 6 x1 x3, okay. Now, if you calculate Hessian matrix of G, what will be Hessian matrix of G? First is del square G of del x1 square, which is 4, then del square G of del x1 del x2, which is 1, and then del square f of del x1 del x3, which is minus 6. Now, since it is symmetric, so these terms will come here. Now, del square f G upon del x2 square, which is 2, and x2 x3 it is 0, again symmetric, this will come here, and what is del square G upon del x3 square? From here it is 4. So, this will be this matrix. Now, what is d1? d1 here is 4 strictly greater than 0. What is d2? The leading principal minor of order 2 cross 2, which is determinant of 4 1 1 2, which is 8 minus 1 is 7 strictly greater than 0 again, D3 determinant of 3 cross 3, which is 4 1 minus 6 1 2 0 minus 6 0 4. When you take this determinant, so this is nothing but 4 8 minus 0 minus 1 4 minus 6 and it is 12. It is 12 minus 4 minus 72, which is negative. It is 32. So, it is negative. Okay. So, one is positive, positive and negative. So, that means matrix is indefinite. Hence, G is neither convex nor concave. So, in the next class we will see that how can we solve some problems if it is a convex programming problem. So, thank you.